year when everything's absolutely chaotic, and I'm sure it's the same for you guys too. So today's lecture is going to be a little bit of some review of what I talked about on the video I posted this morning. We're going to wrap up the course really by looking at biological, by earth sciences mostly, and looking at what it takes to teach earth sciences. I mean, it is a huge amalgam of scientific concepts, and when we're teaching it, often, you know, it's difficult to keep your place within such a broad curriculum. So we're going to talk about what earth sciences actually is, and hopefully that's going to directly feed into assessment task 2 for you, so that you know where you're located in your particular practice of earth science, and also where your digital card is located amongst the other aspects of earth science. And so, you know, the principle here is earth science is essentially 4 different spheres of science. And if you've got a good digital card, and for instance, it's approaching geology, for instance, or it may be oceanography, or it may be a different kind of earth science, you can actually reproduce the same digital card for many, you know, well, for the other 3 branches of earth science. So one digital card can, what we call in technological terms, it can be repurposed. And so that's one of the benefits of doing things in a digital format. You don't have to recreate it. You can simply repurpose what you already have. So I gather from the forums there's a lot of learning going on at the moment about technology in the forums. So I thought I'd start in the forums, and I invite you to stop and discuss any element that comes up here. One thing that keeps coming through, despite the fact that I've responded many times to it, is the dilemma that early childhood education students are facing, where they're looking at this task and saying 2 cards, but there's no prep curriculum. You're absolutely right. There is no, you know, standard early years science curriculum, but there are standard early years pedagogies. So the question to the ECE dilemma is, you know, do we do a prep card? Yes, you do. A prep to year 3 card, and then you can do a year to 7 and 9 card. You can do that. I prefer you didn't. I mean, that the task actually explicitly says to you, you know, to do early prep and early primary. So stick to that if you can. The temptation is to go to 7 to 9, but the task actually requires you as an early childhood student to stick to the early years and the 0 to 3 prep year cards. So, and if you can in the early years, don't worry about the fact that there is no science framework. The goal here is to focus on the pedagogy. There are a range of pedagogies: narrative, modelling, there's cognitive pedagogies, there's the 5 E's, there's POE, there's, you know, a whole range of pedagogies you can use. Focus on the pedagogy, not on the curriculum documents. At no stage, if you look at this task, does it actually say focus on the curriculum documents, okay? But it does say focus on the pedagogy. At the primary level, you will be able to use the curriculum documents to help you locate, but, you know, that's not the whole point of the assessment. That's just an assistance task. A second point that's come up this week is what do we do with teacher instructions for the digital cards? And of course, the aim here is, yes, to put everything you have, your little lesson sequence, your learning sequence, put the whole lot online. Now, the reason here is because you are trying to flip the classroom. Now, flipping the classroom is not about throwing students outside so they're doing things, you know, that you don't have to worry about as a teacher. What it's doing is setting up the inside classroom, your day-to-day classroom, in a way that means students have had an opportunity to come to the classroom with certain of Bloom's lower order functions ticked. So, for instance, you may set a little knowledge quest where students go home and they do a web quest and they learn a little bit about basic plant biology. They can come into the class the next day and they have a little bit of knowledge, a little bit of comprehension, and in the classroom you may have samples of plants that, you know, they go out and collect on a walk, and then you're doing the application stage. So you can see this is flipping the classroom. You know, the whole aim here is not to throw your teaching outside the classroom and download it to parents and siblings and grandmothers and grandfathers. The aim is to make them independent, where they can go and use a resource and they can tick 2 or 3 in some cases. The early childhood probably only going to be knowledge and comprehension, but certainly primary and upper primary will do all 3, knowledge, comprehension and application. The resources are that good that they should be able to use your digital card to do those things. I'll just check and make sure I'm actually recording. I am recording, good. And the third question, anybody want to comment on that one first of all, the teacher instructions for digital cards? Because when you put it online, the child can go home then. You've given it a URL, you've given it a link to a Weebly and a password. Here's a great chance for mum or dad to sit down beside the child. And, here the child can also be the recipient of the knowledge. It could be the consumer of information that you've put up in a digital form. But then the child sits and talks to the parent about what it's doing. And it also then starts to become, it's reconstructing, deconstructing and reconstructing to the parent. The child becomes the more powerful, the more significant other in that relationship. And so this is one of the key ingredients of a got-skin style learning. It really does promote that cognitive domain where the student actually takes on the knowledge, and they often say, as you're probably discovering yourself, the best way to learn something is to teach it. And that's really, that's teaching in a nutshell. Despite having spent years, I spent 5 years doing my undergraduate degree, any time I went into a classroom, I felt like I was learning new stuff. So, it's really important that you as a teacher take that approach, that every time you teach something, you expect to see something new in it. Don't put yourself in that expert role. Comments from the forum, they're saying pedagogies are a very grey area in terms of the cards. They are, but what you need to do is take control of that. Now, this, think about this as a blank page. Your digital card is a blank page. Your whole assignment too is a blank page. In part A, you get in there and you actually nominate which pedagogy you're going to use. And in your 1,000 words, you nominate 2 of them clearly. And in there, we expect to see an explicit justification. That is, you describe your pedagogy, you explain it, you justify, and then talk about how you'll apply it. They're the 4 things you do in that first part, part A. So if you've done that, you can't be wrong. So take away that feeling that it's grey, take away that idea that I don't know what I'm doing, become imaginative now at this point and sort of say, I've said what I'm going to do, now I'm going to do it. And I'm not going to do anything else, this is what I'm going to do. Sure, this may be a little sequence of learning my students are doing, and it may be embedded in a larger unit. So what I'll do is I'll mention what the students have completed before they come in here. I'll then mention our objectives and aims with this particular unit. And then I'll also mention where students will be assessed and where this will lead to in terms of their year level competencies. So you can use all of those frameworks to comment. But by and large, in part A, you describe a pedagogy. You back yourself. You then implement that pedagogy and you demonstrate it. You describe it, explain it, you justify it, and you apply it. That's what you do. So if you can, it's tempting. It's tempting to feel vulnerable in that space. But if you can, put that vulnerability aside, grab this assessment item by the throat and choke it. Literally choke it. Take control of it. 2 pedagogies, 2 digital cards, 2 different year levels, 2 different classrooms with an ICT framework. That's the one thing they've got in common. Simulations pops up too. Okay, we see people saying, can I both tasks have an online simulation? Yes, they do. It's a requirement. Now, why is that a requirement? Let's look at that. It's not because we love online simulations, but because it's really important that you as teachers know how to do this. That, when you're flipping a classroom, no one's going to walk up behind you and say, here's a list of resources you should put in this. As a teacher, you're going to have to free range. You're going to be like the chicken scratching around the yard, around the barnyard, and you're going to be looking for good articles. You're going to be looking for good materials. And once you find them, of course, you're going to keep them. And you're going to have that card that you can repurpose. But simulations are great. And the reason I state this here is it's got to do with the neuroscience of learning. When we talk about brain plasticity, that's what we're doing. We're learning. We're rewiring our brains. And there are 4 distinct stages in that rewiring. The first stage is acquisition, when our sensory realm interacts with the environment. And this can happen in a second. You can walk into a room, you can smell something dead. I had Chris Hoffard, one of my most memorable students. I was teaching legal studies at the time. We were doing law and government lawmaking, and we had this hypothetical class where Chris was this troubled student, and all he did was eat baked beans at lunchtime, and he would fart all the time. So I decided as the teacher, let's address this without humiliating Chris. So we decided to pass the Windbreakers Act, which was all about when is it appropriate not to appropriate in fart and in class. And if someone does fart in class, what would a government do in terms of controlling this? What sort of sanctions, what sort of, social contracts would a government try to create in this particular classroom? And so this went on. The student formed its own parliament and they debated and put together this whole thing about the Windbreakers Act. So they went out there and they acquired knowledge. They collected it. They came back and they rehearsed it. They then looked at different stages, different cases. In other words, they were processing their own thoughts. They then retained it. For instance, we applied different situations. Chris kept eating his baked beans. In the end, he stopped eating baked beans because he lost too many lunchtimes. Instead, he'd do that little thing that kids do when they put their hand under their armpit and they pump their arm to make farty type noises. So then the class had to go back and have a look at their acquisition, their rehearsal, their retention. And they had to go back and retrieve all of that and say, well, why did we pass this particular piece of legislation? What did we learn from it? What was our intent? And of course, in the end, again, they convicted Chris of breaching the Windbreakers Act for making fart-like noises, because the law is all about intent. It's not necessarily about act. So when you're using simulations, there are 4 stages: acquisition, rehearsal, retention, retrieval. Students are collecting knowledge, processing it, keeping it, and ultimately retrieving it for use in future situations, long-term memory. Simulations work fabulously at level 2, rehearsal, and level 4, retrieval. If you want to recover a skill from a student, if you want to retrieve something you've covered previously in the year, a simulation's a great way to do it. If you want them to rehearse some principles, it may be, for instance, the relationship between heat, water, and light in growing plants, then the simulation is a fabulous way of rehearsing how those 3 principles interact and what they mean. And again, just think of computer games. Kids who can play computer games are, if we want to look at Web 2 and Web 3, computer games arguably at some point will replace teachers, in our educational futures. So using simulations, yes, you need to do 1 for each card. And bear in mind, it's got to have a pedagogical relevance. It's got to fit in there to the acquisition, rehearsal, retention, or retrieval stage. And my argument here is it's probably going to fit in rehearsal and retrieval much more easily than it will fit in any of the other 2. Moving on, anyone want to comment on anything I've said so far? Okay, please just interrupt if you will. This is the final session. I'd really like you guys to take it over. I mean, this is the last time we'll be chatting online this term. So please, at any point, jump in. So other things coming from the forums, locating the digital cards online. There's a little bit of tech phobia emerging, a little bit of technology phobia emerging online through the forums. The assessment item does request you and require you to embed your digital tasks in an online or digital digitally retrievable setting. Now, some of you, for instance, are using Blogspot, some are using Wix, some are using Weebly. And I do believe you used Weebly in a previous course. I'm new to CQU, so I'm not quite sure what that course is, but I do believe you have had access to using Weebly. In Education Queensland, where most of you will finish up teaching, Weebly will not run on EQ servers and systems. It is blocked. But in most of your schools, you will have a simple file system where you'll be able to create a file online. It'll be a share file, and everybody, all your learners, all your children in your class will be able to access that as they would any online repository. The only thing is, of course, it's not available 24/7. But for instance, what I did always when I was working with Education Queensland was I always created modules that were downloadable so kids could just plug in their USB codes and take it home. So, but it is a requirement that you drop your digital cards online for retrieval, because obviously, when you put together your little table, make a hyperlink to it. I'll jump in there and have a look at just how well a learner would experience your digital intent. Because let's face it, you're sending them home to be independent, and your digital card really needs to work. It really needs to work and be suitable for your audience. And that brings us to our point about the early childhood digital cards. It must be printable. You're facing a limited reading age for the end user. And, many of you have completed the subject multi-literacies, where you look at literacy as particularly digital literacy. We look at a hyperlink and we can understand what it means. This means it connects to a richer source of knowledge. Icons often are little pictorial activities which suggest an activity rather than a word. Those words, and this is what Wittgenstein in 1920 talked about. It's his theory of language. When we have a word, we form an image. And from that image, we form derivative words. So when we think of mum, we think of dad. When we think of dad, we think of family. When we think of family, we think of grandparents. When we think of grandparents, we might think of home, or we might think of old people. There's a range of schemas we could go in there, but Wittgenstein nailed this in 1921. This is not a new theory of language. In your digital cards for early childhood, use some of Wittgenstein's ideas. Use icons, use mnemonics, have context cues, use very simple language, simple sentences. And bear in mind, these instructions have to be suitable for an independent user to go home and adopt. So don't rely on them sitting down with a parent when they get out of the classroom. Don't flip the classroom to somebody else. Flip the classroom to the learner. Make it learner-centered. And the final thing that's come out is some really good questions about, and some students doing some brave stuff out there. I really, really appreciate some of the efforts you're making to adopt Voki and a whole range of different software. Bear in mind the limitation there is A, it may not run on Education Queensland servers, or it may not run on Early Centre servers, or it may be locked down in most schools. Secondly, what you'll get is a 7 to 14 to 20-day trial of that software. Beyond that, that software won't work. So I know this task is due on June 1st, so you're probably safe. But if you did it 2 weeks ago, come June 1st, chances are your trial period is over. And when I go to link into your assessment, what would happen would be that I would be locked out and I would not be able to assess your work. So don't use a tool just because it looks like a fun tool. Okay, toolishness is foolishness. The time to use it is when it adds pedagogical value. Does it help you flip the classroom for the better? Is it sustainable? Will the license expire or be blocked? Does it suit the learner? Is it age appropriate? In other words, if you're having difficulties using a piece of software, how's a learner going to travel? But if you can answer a strong answer to yes, to 1, 2, or 3, then you have a good ICT transformation to include on your digital tool. Okay. Can you take it to the university to get students access to Google Classroom? No, I'm not using Google Classroom. I know Google Docs. I know Dropbox is generally accessible. Anybody like to comment on Julie's query there on the chat? No comments? No one knows. I don't know either, Julie, so I can't help, but I'll certainly investigate that one and try and get back to you on the forum. Some really good resources that don't take a lot of adaptation, for instance, are ones like TED Ed that I actually showed you last week, where you can jump on and you can research a lesson in thousands of curriculum areas. If you look at those lessons, you know, it really does create very Bloom-like interaction where they go in and the first interaction they have is they create knowledge. The second is they engage in comprehension. And the third is they look at real-world applications. And the final thing is they can actually get into a discussion group and they can start to really embed that knowledge. So TED Ed is a really good one if you don't want to, you know, build your own and just look for something that is embedded online. Anybody got anything else they'd like to raise before we leave the forum discussions? Okay, we'll leave the forum discussions and move on. I am recording this today, so I will post it. So what I tried to do this week is talk about what is earth science. Because the temptation is when we talk about earth science is to go all red raggy and sort of environmental. And while that's great, I am a red ragging environmentalist, it's also got to be done in a balanced way. The two great questions facing our generation at the moment, facing your generation, I mean, mine's coming to an end. I'm in the last third of my life, but the reality is for you guys, the questions going forward, the dominant paradigms, the economic bottom line and the concept of growth and development. So in those two major narratives or meta-narratives, we are looking at some significant challenges for earth science and ways in which we can teach a cohesive earth science message so that we can promote sustainability and that we can promote balance. Now, from a purely knowledge perspective, Loxley does a reasonable job in chapter 11 this week in teaching some basics. But, you know, I'd prefer Aristotle's version than Loxley's. Aristotle bestowed on us the obligations of citizens, that we must be citizens in our lives, and citizens in lively citizens, active citizens, take part in the Senate, in the human Senate. And the Senate is what preserves the community and in Greek tradition. Now, as teachers, we're part of that teaching Senate. We're part of that collective. And our role very much is to be over the top of earth sciences in ways that are going to enable us to teach and deliver an earth science curriculum that is cohesive, that offers every student in our classroom, regardless of whether they're the son of miners in a mining cartel or whether they're the daughter of children in Corandon, north of Cairns, whether, you know, whatever their political and environmental perspective, we've got to offer them a way to deconstruct that and reconstruct it in a Bloom-like way. We've got to offer them ways to create real knowledge, real comprehension, and real application that falls outside their lived experience, because that's education. Lived experience is not education, that's ideology. Even if it's a good ideology, we need to give them the tools they need to make it a better ideology, to ground it. So what is earth sciences? So by the end of this week, we had four clear aims, and I think just browsing through Loxley, you'll just get those quite well. Identify different types of energy. It's a fairly modest aim, isn't it? Renewable and non-renewable. Various sources of energy. You know, there's 4 large basic sources we can look at. Compare and contrast these new renewable and non-renewables. I mean, that's fairly easy to do. And explain global warming. Now, scientists struggle with that, so it's going to be a challenge for us as teachers. So what we're doing here is moving in that final goal towards an inquiry-based approach. Okay, and here's where it's a real opportunity, it's a real invitation. So when we look at what is earth sciences, it's an amalgam of 4 scientific genres: geology, oceanography, meteorology, and astronomy. So as you can see, you know, each of those have a different history. Geology, oceanography is an emerging science. Meteorology, okay, again, quite an emerging science, the discovery of new planets and solar systems. And astronomy, of course, both new and old, in fact, new and ancient. We can look at our Indigenous communities globally and locally to see their connection to astronomy and, you know, the meaning of astronomy in their lives as an organising structure. So we can see that it's a really rich area, earth science. It's a broad area. It's incumbent on us as teachers to have a really good teaching structure. If we don't, we could look really ineffective here. We could look like we're just adding fluff to an existing fluff ball. So it's really important that we help deconstruct existing ideologies and lived experience, and we help reconstruct knowledge, comprehension, and application. So what do? We know about the formation of the Earth, and we have consensus here. Now, Loxley talks about this. The planets, the solar system form roughly the same time. The hypothesis is the nebula hypothesis. And here it is in its 5 basic steps. Now, my goal here is not to educate you in earth science, but to give you the tools. When you talk to students, come from a common place. Create a common language. This is what we can do. For instance, one of the great tasks is, you know, to sit down with students and lie and do some cloud painting. I used to do it with my children. We'd lie in a big green paddock and just cloud paint, sometimes for hours on end. And we'd look at what clouds formed over, and we have these really great discussions about where we came from and how the world formed. And I remember one morning my youngest daughter came in and sat on my bed, and I was having a cup of coffee and reading the newspaper in bed, as you do, you know, on your Sunday mornings. And she said to me, "Dad, I've got a question for you. Where did I come from?" And of course, I thought, I knew she'd ask me this one day. So I started talking to her about the birth of the planet and human nature, and about men and women and love and passion, and even, you know, hinted towards the fact that there's a thing called sex, and children are born from that. And as a result, you're here, you know. And I looked at her with a big smile, and she said to me, "Oh, okay, thanks, Dad. Just Tiffany comes from China. I was just wondering where I came from." So sometimes it's really important to get back to a common language. And that's why I tell you that story. I mean, I was off on my own tangent. What she really wanted to know was where she came from, which country, which place, which town. So that would have been answered much more simply. The nebula hypothesis. Build yourselves a language. So when you say we're doing earth science for the next term, all of a sudden pull on your earth science clothes, feel really happy, pull on your language, dust it off, pull out your old repository of resources, enjoy it. Formation of the Earth. I put up a little video this week called Earth the Movie. I actually play it in the video I posted online this morning. The reason why I did that is actually just download it from YouTube. It's really a very common video, and it's also actually factually accurate. The reason I play it is because the music's great. And here we're talking about multimodal learning. When we're talking about the planet, all of a sudden we want to blow their concept up. We want to explore it. We want to actually say to you, you're going to let go of what you think you know here. We're going to separate you from your experience and your assumptions. And what we're going to do is we're going to imbue it with a whole lot of rich context. And so the music does that. It actually helps separate the student from their cognitive beliefs. That is the benefit of multimodal. And we can see, for instance, we could tell them about the decay of radioactive elements and heat, high velocity impacts, increasing temperatures, rocky components forming gaseous material, or we could show them a movie. We could show them a movie, and then we could ask them what they saw. And then we could apply the language. We can apply the language of earth science to say, actually, you know what? This is what you saw. This is what we all saw. What did you think of that? Can you draw it? Can we build a model? Can we build a model of the nebula at 1, at 2, at 3, at 4, at 5? Okay, all of these different things. Earth is, we can break it down. It's really important to break down earth science. We can break it down into 4 basic constructs here, or what we call 4 major spheres. There's the hydrosphere, the ocean, and it's a rich field, particularly for us here in Townsville, for people in Cairns, Mackay. It's the most prominent feature of the hydrosphere. It's relevant to us all. About 90%, 7% of the Earth's water. So again, in there's a little inquiry task. What's the other 3%? It also includes freshwater and streams, lakes, glaciers, as well as that found underground. So anyone, for instance, who goes inland from Cairns and Townsville, I can't remember the name of the town now, but it actually has an underground river running directly below it. And where it draws its own water supply from. On the top, it's dry as a bone. It's sand. Underneath, there's a rapid flowing river. Just brilliant. The other spheres, atmosphere. Okay, something we don't think about a lot. The thin, tenuous blanket of air, basically split into half, 5.6 kilometres above the Earth. We have the upper atmosphere. Below that, we've got the lower atmosphere. Go figure. Who knew that? The atmosphere has actually got 2 parts. Wow. What can we do about that? How can we explore that? Biosphere, all life. Concentrated near the surface in a zone that extends from the ocean floor to several kilometres up into the atmosphere. That's the biosphere, the creatures. The geosphere is the final we come to, based on compositional differences. The Earth itself, the physical makeup of the Earth, the crust, the mantle and the core, 3 basic parts. Jules Verne, Journey to the Centre of the Earth, written I think it's Jules Verne wrote in the 18th or 19th century. Predicted a lot of the science we have today, actually. Everything from tasers. Tasers first appeared in a Jules Verne novel. So there's so many things that we can actually explore when we look at this, and we actually start to dissect the Earth's major spheres. So when you're arranging your science curriculum and you're teaching Earth science, the question is, which Earth? Which sphere? What do you know about it? How can you compact that language? How can you speak it essentially and effectively to others? We can look at the Earth as a system, and we can see that the Earth is made up of a range of different systems. Here we've got, for instance, you know, the what we call the geological system or the geosphere. We can talk about plate tectonics, the shifting, the formation of the planet over time, and countries and nations, and the determining of location, longitude and latitude. Maps and mapping, the evolution, you know, going back to Ptolemy's world of the map, a map of the world, which the first ever attempt to really capture the world as a single entity. And believe it or not, it was flat, Ptolemy's map of the world. And, you know, we can question that. And here's a fun task for someone who wants to take it on in a class. If you Google the Flat Earth Society, you will see that there's still a profound amount of people who live on planet Earth who believe the Earth is flat. So there is a Flat Earth Society, and what a great way to introduce maps and mapping and topographic maps. You know, Google the Flat Earth Society. Who are they? What do they believe? And why do they believe it? And then a unit on, is the Earth flat? How do we know? Okay, fantastic stuff, all inquiry driven. Oh, sorry, I just meant to go back there. I talked about the system being any size and comprising two parts, closed and open. And the same with the planet. There are closed aspects of our planetary systems and open systems. And hence, closed systems are much more manageable, although, and more sustainable, arguably. Open systems do pose what we call environmental threats, and we'll come on to that in a minute. So Earth system, what we're saying is Earth is a dynamic body with many separate but interacting parts or spheres. Earth comprises numerous parts and subsystems. And the sources of energy we can talk to, there are two basic sources of energy, external or internal. The sun creates weather, ocean circulation, erosional processes. The Earth drives internal processes, volcanoes, earthquakes, and mountain building. Now, what we're doing here, and this is not a detailed lecture. What this is a concept mapping exercise. What we're trying to do here is work out what we mean by Earth science. And if we are going to teach Earth science, we need to locate ourselves as teachers and as humans in there. So we are one part of the Earth system, and we're subject to the energy cycles driven by the sun, by our external processes and our internal processes. And therein lies people and the environment. So we can look at ourselves as, as subject and living under our atmosphere. We could talk about our environment as something that surrounds and influences organisms. We know it's got physical components, water, air, soil, rock. And when we talk about environmental, it's usually reserved for those aspects that focus on relationships between people and the natural environment. Now, another true story, when I first moved to Cairns in the year 2000, my partner Lynn was taking long service leave from her job as a psychologist and decided to do something different. She started a cafe in Cairns called the Lily Pad Cafe. Now, anyone who is distant student in Cairns will know the Lily Pad down on Grafton. It still exists, and it's very, very popular. It's an alternate cafe. Great, we opened it as a vegetarian cafe. It now does Tex-Mex, and so still a lot of vegetarian food. But the whole purpose we opened that is to do something a little bit different. We decided to make an environmental statement, so we used all biodynamic products. We tried to go totally green, and one of our most popular customers, of course, was Peter Garrett, who then he wasn't a politician yet, but he became a Labor politician. Then he was an ex-rock star and, of course, a nuclear activist. And ironically, instead of having table numbers, we had pictures and stories of environmentalists and activists. And every time Peter Garrett came in to order a meal, he would come in and grab his own picture, which is quite a comment on Peter Garrett, I thought. But there you go. So when we talk about environmental, we're talking about relationships between people and the natural environment. Resources, water, soil, minerals, and energy. And again, here's the two types of energy we're talking about, renewable and non-renewable. Energy is a resource. We can look, next term we'll talk about chemistry and chemical reactions and processes, and the notion that, when we use resources, they don't disappear, they simply change energy forms. So we'll look at that next term, and we'll look at more science around that. So we will come back and visit resources in some degrees, in some ways. But we know, for instance, and here we're getting into some of our curriculum substrands, plants, energy, water, wind, non-renewable, our carbon-based resources. So we're seeing here now, all of a sudden, if nothing else, it's really important that we start to have a look here at how Earth science strings together. Where you are, how far, which sphere you're in, which system you're talking about, which type of energy you're using, so that at any time, as a redirection or as a rethink, you can send your learners back in a different direction. We can look then at environmental problems. Why does the planet fall out of balance? What is it about our use of energy and the balance between our environment? And we can explore it on local, regional and global levels, which again is really, really good to do, because we can look, for instance, and look and see what's an issue locally, how that's managed regionally, and whether it applies globally. And it gives you three different ways of looking at the same problem. So for one body of science, you can actually create three different lenses for looking at it. And we can look at some of the problems we create, which are well captured here in this little chart put up by Linda Pfeiffer when she did this material originally. We can look at the urban air pollution, acid rain, ozone depletion, global warming. Some of the things not listed there is urban sprawl and urban density and crowding. And of course, this whole concept of psychological health. when you live in a dense urban environment, the number of issues, number of stress, concepts like domestic violence, and it's a really touchy topic to raise with kids, but we can see what urban density does to people. And there's a fabulous New Zealand movie for any Kiwis in the group who watch this called Rat Park. Just Google Rat Park. And it's done by a psychologist. And the psychologist actually explores what happens when we change the environment in which rats live, which is great for a study of growth of the world's population. What happens when we change the environment? That is, if we take them out from a crappy little rat enclosure and we actually put them in a lovely rat enclosure where we paint murals, where we provide plenty of food, where we create lots of burrows, where we have plants and overgrowth. And believe it or not, the rats thrive. The violence amongst rats decreases. The cannibalism amongst the rats basically disappears. We start to see rat colonies multiply at 3 times the rate they would under their normal conditions. So again, it's a form of experiment, but it's called Rat Park. And if you've got an older primary group, they love it. They absolutely love it. Okay, it's fabulous watching what happens to these rats and what they do when their environment changes. And of course that raises the whole question then, an inquiry task. What if we changed all of our environments? What if we worked on building environmental solutions to most of our problems? Scientific inquiry. The final point I want to make before we finish this slideshow. Once we've done our systems, once we've done our spheres, once we've done our energy sources, we've located ourselves. And then we can actually look at our concept of environment, and we can look at the human, environmental, and scientific interactions. We can now start to explore those by applying inquiry. And this is what assessment task was all about, assessment task 2. Science has this assumption, and bear in mind, we go back to the natural sciences. Okay, in the 1800s, that was actually a very, very small field. The largest science in the world in the 1800s was philosophy. This continued into the 1900s. Believe it or not, medicine in the 1900s was considered to be an art. It came from healers, from shamans, from witchcraft, believe it or not, many of whom were burnt in the 11th and 10th centuries. It survived, had a renaissance in the 17th century. But what we see largely is medicine as a science was really an art form. Okay? It was done by shamans, by healers, okay, and was not considered to be a science per se. These days, of course, it's changed dramatically. Everything tries to replicate medicine. But science used to assume that the natural world was consistent and predictable. What the Latin term we use is ceteris paribus, that is, everything held constant. So science assumes that the world is constant. And therefore the goals of science are really, of earth science, are discover patterns in nature. And then we use what we learn from those patterns to predict what might happen to nature given certain variations. Now this may sound like I'm talking to the converted, but how long since you actually sat down and said to yourself, why am I teaching science? What is this whole unit been about? Here we are in week 12 or week 11. What have I actually understood here? What am I going to impart to my learners? So the goals of science is to seek out patterns and to use that knowledge to predict future patterns. So an idea then can become one of two things, an hypothesis. This is not new. It goes back to 19th century science, where we get tentative or untested explanations, and then we come up with experimental designs to test them. The idea can then become a theory if it survives the test. But we know Karl Popper, and Popper said that every theory is just simply an untested or a non-proven hypothesis, or a non-disproven hypothesis. So a double negative there, very hard to get your head around. But he was arguing that, every theory is just waiting to be disproven or unproven. And so scientific method and scientific knowledge, we gather facts through observation, and we can do this with our students. Here's our classroom, here's our pedagogy. They can formulate hypotheses, and we can test hypotheses to formulate theories. Do we need to know a lot about science to do this? No, we don't. All we need to know about inquiry, the stuff that teachers do, Vygotsky, Piaget, all the great cognitivists. We need to know those cognitive processes. We go out and we collect knowledge. We develop a hypothesis, and we comprehend. We conduct experiments, we apply. And then we re-examine the hypothesis, accept, modify, or reject it. Okay, and there blooms 3 higher level functions. So we create scientific knowledge by following systemic steps. We also create theories that withstand examination. If they do, says Karl Popper, it's a theory until we prove it wrong. And also, scientific knowledge creates totally unexpected occurrences. And we know this from science. You know, Madame Curie discovered penicillin by accident. You know, there are so many explorations within science that have been accidental discoveries. So our aim when we teach science is to create the environment for the unexpected. And also to create an environment for exploring what we think we know and challenging that. So what do we teach? Do we teach facts? There's a lot of facts there on that page. There's lengths in kilometres. There's names, stratospheres, tropospheres. There's CFC molecules. There's ozone molecules. There's their interactions and depletions. There is a story there that we could tell people. We could turn it into a narrative. We could create them to write a fairy tale. We could get them to write a song. This is all science. We could get them to write a myth. We could explore existing myths. We could then look at the scientific explanations. Scientific inquiries. We could look at classification. For instance, here's a classification map based on rocks, on the structure of rocks. We could present that to students and simply say, why? Why would rocks need to be classified? Here's another one for planets. And we can see just by some of the names there, white dwarfs, red dwarfs, this is a really rich task. Why is this the way it is? What are scientists trying to do? Why does science use models in this way? Over here we've got a little prism. Length by width by height equals volume. How do we measure volume? With a ruler. Really simple. Science is accessible. The whole notion of mass, the way in which we measure mass is using scales. Okay, it's a formidable way of measuring mass, simply by weighing items. And the weight, of course, can be measured in a range of currencies. It can be in millimetres, millilitres, or cubic centimetres, a whole range of ways of capturing mass. A couple of little questions for you. If an object is heated, what happens to its mass? Does its mass actually change? And the clue to that answer is in the atomic structure. When you heat something, its atomic structure actually doesn't change. So its mass doesn't change, it stays the same. And if we know about Earth science, if we have our little schema in place here, we can roll out possible answers. If not answers, it's not our role to answer everything, but we can actually rephrase the questions and create the questions that we want students to learn and ask. Another little question, how do we measure volume? Length by width by height. Okay, but what happens if we get an irregular thing, like we pick up a big rock and a small rock, and we say to the students, what is the volume of this rock? And they get a ruler and you watch them trying to bend their ruler around. Some will be clever and get a piece of string. Okay, what we do is we get a beaker. We get a beaker which is actually lined, measured, and we then drop the rock in the beaker. We fill the beaker with water to a certain level, to the top of the beaker measure. We withdraw the rock and then we measure the drop level, and the volume of that rock is that measure in millilitres. So we can measure any rock of any shape. We're amazing scientists. Okay, we're scientists in our own lives. We can, instead of teaching content, we can teach relationships. Here are two variables. Two variables, one called population and one called pollution. They have a direct relationship to each other. A couple of different relationships cited here. Here's a direct relationship. So as the population increases, so does pollution. As the distance from the sun increases, for instance, so does the number of revolutions of a planet. Here's an indirect relationship. I want you to think of that. Put on your science hat here. What does that red line sloping backwards mean? It actually means, for instance, that we could look at the distance from the sun and gravity pull. Okay, the further we get from the sun, the less the gravity. We could look, for instance, at climbing Mount Everest. The higher we get on Mount Everest, the lower the temperature. So we can actually hand these graphs to students and say, we want you to come up with, probably an upper primary task, with 4 inquiry tasks that represent these graphical relationships, express these relationships. Here's one on prediction. What can we tell from this? Now, anyone who's watched the video from this morning, there's a whole range of things that fit in there. It can be the phases of the moon, quarter moon, half moon, full moon, all the way back down again. It can be sunspots. We can chart sunspots through telescopes. The tides, the seasons, all of these lead themselves temperature within a month. Okay, all of these lead themselves to graphical predictions. Rainfall, thank you, Nicole. Excellent one. Something we rely on a lot here and in our communities. Here's a flat line. What does that mean? This graph is dead? Probably signifies no relationship. So this could be, for instance, the tea in China versus the tea in America, or tea consumed in China versus tea. There is no relationship. Okay, and we could look at a whole range of different things. So it's not, therefore, it's not a scientifically valid relationship, is what we conclude from that. So we could throw these to students instead of throwing them a book. We could throw these to students with some subject suggestions and say, come up with some environmental issues which have the following sets of relationships. Of course, you'd have to teach about the relationships first. You'd have to build knowledge. You'd have to make sure the comprehension was there, phase 2, and then you'd send them off on application. And then you'd create some research tasks for them. And of course, we're seeing them fly along Bloom's taxonomy, and they're becoming totally independent. They're becoming the dominant or the featured person in the ZPD, the more capable other, and we're starting to see science really coming to life. Some more examples. We can see here humidity versus temperature. It's a predictable curve. Here, for instance, we've got a nice linear one between erosion and soil relief, okay, as we can see there. And some others that we've listed here probably are density versus weight. Density is a really interesting one. What happens when we take an object and we heat it? What happens to its density? What is density? Well, density is the atomic structure of an object. When we heat something, of course, its atomic structure loosens. The atoms don't depart, so it weighs the same, but it loosens. It becomes more liquid, more fluid, more vaporized. As a result, of course, it's going to have a looser density, but its weight will still be the same. Hence, we can melt something and its weight will still be the same, of course, allowing for evaporation. So these are scientific principles. This is what we're talking about, trying to take earth science, trying to turn it into something that is not ideological, but to bring it back to that inquiry framework. And that is the challenge of teaching earth science. You know, and of course, by all means, as long as you're doing that knowledge, comprehension, application stage, then students are free to go ahead in the remaining 3 stages of Bloom's taxonomy to really evaluate that knowledge and evaluate what we're doing, and then start to form positions for themselves. Start to identify their own knowledge and their own value structures within that scientific field where they sit. That is who they are as a scientist within that field. But they're higher order functions. We don't want them to start there. As teachers, we want to give them the skills that will take them through life at those basic levels, knowledge, comprehension, application, where they can apply it to any situation they come in contact with. I'm going to stop there and open to you for questions, whether by chat or by microphone. I welcome anything, please. It can be related to anything.